Hello, fellow problem solvers. So today we're going to be doing a problem from the 2008 IMO shortlist, problem number N2. This is a fantastic number theory to try to solve if you feel comfortable enough in your number theory skills and you want to try an IMO problem to test them out on. I would suggest for this one taking a minimum of an hour and a half, ideally 2 to 3 hours, but not more than 3.5 hours, if this is your first number theory problem from the IMO. On the other hand, if you'd like to go along with us, I suggest you take 30 minutes and put your first ideas out on paper. So now, let's begin. So the problem statement is basically this. We have a1, a2 through an, distinct positive integers, n is greater than or equal to 3, and we must prove that there exist I and j which are different, such that ai plus aj does not divide 3 times ak for all k 1 through n. Now the first order of business is, if you want to prove there exist these such that this doesn't hold, let's assume the contrary. Let's assume that for every i and j, which are not equal, there exists a k such that ai plus aj divides 3 times ak. Now take 5 to 15 minutes and see what would you do here. Well, the next thing I would do is I would say, okay, let's assume without loss of generality that a1 is greater than a2 is greater than till an. Now that I have this thing without loss of generality, also if you haven't done this, take another 5 to 15 minutes and see what you would do next. For me here, I would be thinking about a1 plus a2. Which number will it divide? And this is just me thinking out loud. And the reason I want to pick a1 plus a2 is because their sum is the biggest. So it will be the biggest divisor. And it is bigger. a1 plus a2 is bigger than 2 times ak for all k. So if it divides 3 times ak for some k, then what we know about this is that a1 plus a2 is equal to 3 times ak for that k. Now with this, I would invite you to take another 5 to 15 minutes, pause, and push the problem further. What would you do next? So my thoughts here are, I have this thing for a1 and a2. And what happens when I take a1 plus a3? What is going to be this? It divides 3 times al for some l. What can this be? And now I'm also thinking of going a1 plus a4 and a1 plus an. Like, these seem like interesting numbers, pairs of I and j to look at. And the reason I find them interesting is if I take a1 plus ak divides 3 times al, then I know there exists a d such that da1 plus ak is going to be equal to 3 times al. Now what I know from here is that d is less than or equal to 2. Can you tell why? Take a minute to 3 minutes to figure out why d needs to be less than or equal to 2, no matter what k and l are. And the reason why is simply because if d was greater than or equal to 3, then we would have 3 times al, which would be equal to da1 plus dak, would be greater than or equal to 3a1 plus 3ak. And this would be strictly greater than, because a1 is greater than al, 3 times al plus some change. 3 times al is greater than 3 times al, a contradiction. So that means d must be always less than or equal to 2. And now I have this pretty nice thing right here. For all k, d is less than or equal to 2, and a1 plus ak times d is 3 times al. Now this is also the reasoning why I took a1 with any other number. Is because if I took, say, a2 plus ak times d is equal to 3 times al, l could be 1. So this is a lot less general. Like, there aren't, perhaps, or maybe there are, many of these k's, like maybe a2 plus a3 times a2 plus a4 plus all the way till a2 plus ak is actually what a1 is. So I wouldn't be able to say what d is less than or equal to, but I have some sort of estimate for how big or how small d actually is. Now with that in mind, I invite you to take 10 to 30, even 45 minutes. I would take an hour if this is your number theory problem that you want to solve at the IMO level. Take that time before you go to the next step. Here's what I would do. Okay, so now we have this, and these always 1 or 2. Now, one thing that you could be thinking of doing, okay, what if these always 1? What if it's 1 half of the time, 2 half of the time? How do these k and l talk to each other? Is l greater than k? Is k greater than l? Or is ak greater than al? Al greater than ak? What is happening here? Those are all ideas I didn't take quite yet, because the next thing that came to my mind is, wait a second, d is 1 or 2. This means that 3 divides a1 plus ak for every single k, because for every k there exists an l. That means that for every single k, 3 divides a1 plus ak. Now from 3 divides a1 plus a2, 3 divides a1 plus a3, all the way till 3 divides a1 plus an. What do you get from here? Well, what you get is that a1 is congruent to negative aj modulo 3 for all j not equal to 1. Now, if 3 divides a1, that means it divides every single other number in this list. On the other hand, if 3 doesn't divide a1, it means it doesn't divide any other number in this list. Take 5 to 15 minutes and see what would you do with this insight. And here's the next sort of big idea is, this is a general tip in number theory, is that because this is a homogeneous, meaning they all have the same power, equation we have here, we can assume if, say, all these numbers, if their greatest common denominator was, of all of them, of a1, a2, and an, was some number, say, d. Then if we plugged in a1 equal to b1d, a2 b2d, an bnd, where the greatest common denominator of b1 through bn is 1, what we would get is that the same problem condition would hold. Nothing would change here whatsoever. It's a different d from this one, but nothing would change whatsoever. And we would have an extra condition, namely that the greatest common denominator of all the numbers is 1. This is also a thing you will use if you ever do something like infinite descent. This is a shorthand for not having to go through infinite descent in number theory. If that doesn't mean anything to you, no worries. The only thing really that matters is, and it's also not a very complicated idea, the only thing that matters is this right here, that we can assume really, for all intents and purposes, that the greatest common denominator of all these numbers is equal to 1. Now, what that means is if their greatest common denominator is 1, that means all of them can't be divisible by 3 simultaneously, which means we can take the other case, without any loss of generality, that 3 doesn't divide a1, which in turn implies, because of this, that 3 doesn't divide any one of these numbers. So what you get from here is that all of these numbers are either 1 or negative 1 modulo 3. And in fact, there's 1 or 2 cases. Either a1 is 1 modulo 3 and all the other ones are negative 1 mod 3, or a1 is 2 or negative 1 mod 3 and all the other numbers are 1 modulo 3. Now why does that matter? Well, it matters because if we take a2 plus a3 divides 3 times as, because a2 and a3, a2 plus a3 is relatively prime to 3, this means that a2 plus a3 divides as, that we can infer from here, we can infer this. Now with that in mind, I would invite you to take another 5 to 15 minutes and see how far you can push the problem now, given this new insight. Now before I continue forward, I'm going to give you one insight that I got when I was trying to solve this problem. It's a question I asked myself. What is the sequence which almost satisfies the problem statement? And the sequence which almost satisfies it is a1 equaling n, a2 equaling n minus 1, all the way till an equaling 1. Now, ai plus aj divides 3 times ak for a lot of these. Actually, wait a second, I'm completely wrong. This doesn't really satisfy the problem. Bad idea. And this is an instructive moment as well, because you will be getting bad ideas when you try to solve a problem. And getting a bad idea is not a bad thing. It's just another thing. It's another thing we searched And we figured out this didn't lead to a solution. This was a dead end. And now we come back and get a new idea. And here's what that is. We have this. And we also have that a2 plus ai divides 3 times aj for some j, which means that because a2 plus ai are both either 1 or 2 mod 3, that means their sum is going to be relatively prime to 3. And from here we can infer that a2 plus ai is equal to aj for some j. So for each I equaling 3, 4, all the way till n, there exists a j equaling 1, 2 to n, such that this is true. Actually not this, but rather that this divides this thing right here. Now what this tells us is for each I there is such a j. Maybe take 5 to 15 minutes and figure out what this tells us. Well, the question is really, what can j be? You see, aj, because it's divisible by a2 plus ai, and a2 is the second biggest one here. We know by divisibility that aj is greater than or equal to a2 plus ai for each I. And because ai is greater than 0, this is greater than a2, which means that j is equal to 1, which means that a1 is divisible by a2 plus a3, by a2 plus a4, by all of them, a2 plus an. Now getting to this conclusion, the previous thing where I said a1 could be incredibly large, the multiple of all of these, seems like foreshadowing. Now given a1 is divisible by all of these, we know that a1 divisible by a2 plus ai. And now what can we do with this? I invite you to take another 5 to 15 minutes and try to push the problem further. And the next sort of idea is to come back to the original thing, is a2 plus a1 divides 3 times al for some l. Now what can this l be? Well, we know that we have this inequality just from divisibility, 3al. Now here we know we can estimate this, maybe put it as a2 plus 2al. And what this gives us is a1 is less than or equal to, actually strictly less than or equal to, because this could be a2, to al. Now, there seems to be a problem with this and this at the same time, because if a2 plus al divides a1, that means this is less than or equal to a1. And now we could get this is less than or equal to al plus a2, and this is less than or equal to a1. Now the equalities only hold if l is equal to 1 or 2. Now what does this mean? It means that a2 plus a1 either divides 3 times a2 or 3 times a1. Now take 10 to 20 minutes and try to finish the problem up. Here's the next step. We have this, and now we break it into cases. If a1 plus a2 divides, say, the smaller one, 3 times a2, then we have d times a1 plus a2 is equal to 3a2. Now, if d was equal to 2, then we would have 2a1 plus 2a2 equaling to 3a2, which would imply that 2a1 is equal to a2, which is a contradiction because a2 is less than a1 and these are positive integers. So that means that this would imply d equaling 1, and with that a1 plus a2 would be equal to 3a2, which would imply that a1 is equal to 2a2. Now take 5 to 10 minutes to figure out the next step, and the next step is, now we know that from a2 plus ai divides a1, we can rewrite this as a2 plus ai divides 2 times a2. And now from here, when we subtract 1, we get a2 plus ai. When we subtract this once, divides a2 minus ai. And because this right here is less than this, and it's not 0, in fact, it's greater than 0, this provides a contradiction, because this number cannot divide this number. So in this case, right here in the case that this divides 3 times a2, we are done. So let's look at this case now. a1 plus a2 divides 3 times a1. Okay, so we have plus a2 times d is equal to 3 times a1. And from here, if d is 1, we would get 2a1 is equal to a2, a contradiction. And if d is equal to 2, we would get 2a1. So we're left with no a1s here. 2a2 is equal to a1. Wait a second. Oh yeah, that's the same thing we got here. And we would proceed to solve this in the same way. Now I invite you to just take 5 to 15 minutes and wrap up the problem, connect all these ideas together, and write down a solution. Here's the full solution. We start off by saying, without loss of generality, the greatest common denominator of all these numbers is 1. And then also without loss of generality, we say a1 is greater than a2, greater than all the way till greater than an, and greater than 0. We also then assume the contrary, namely this: for every I and j which are different, there exists a k, such that ai plus aj divides 3 times ak. So our first step is that a1 plus ai divides 3 times aj for some j, and that implies that there exists a d such that dA1 plus dAi is equal to 3 times aj. And now, if d is greater than or equal to 3, then we would have that 3 times aj would be greater than 3 times aj, which is a contradiction, which means that d is less than or equal to 2 for all I. Now this means that from d times a1 plus ai equaling 3 times aj, this means that 3 divides, because 3 does not divide d, it means 3 divides a1 plus ai for each I 2 through n. Given that the greatest common denominator of all these numbers is equal to 1, this means that a1 is not divisible by 3, because otherwise ai would be divisible by 3 for each I. So from here, we know that 3 doesn't divide a1 times a2 times an, because if it divided one of them, it would divide a1, and then it would divide all of them. Now from here, what we know is that a2 is congruent to a3 is congruent to all the way till an is congruent to a negative a1 mod 3. And this means that ai plus aj for ij greater than or equal to 2 is not divisible by 3. It does not share any factors with 3. And from here, we get to our second step, namely, for each I greater than j greater than 1, there exists a k such that ai plus aj divides a k. And we know this because there exists a k such that this divides 3 times a k. And given this, we can infer it divides a k, because it doesn't share any factor with the 3. And now we get to the next step, mainly a2 plus ai divides aj for some j for every I. Now this means from a2 plus ai less than or equal to aj, this means that aj is greater than a2, and because it's less than or equal to a1, we know that j must be equal to 1. So a2 plus ai is less than or equal to a1. In fact, it divides a1 for each I. And now from here, we move on to our final and fourth step, namely, a1 plus a2 divides 3 times ak for some k. We know that this implies that a1 plus a2 is less than or equal to 3 times ak, which is less than or equal to 2 times a2 plus ak, which in turn implies that a1 is less than or equal to a2 plus ak. But we know that a2 plus ak divides a1, so it's less than or equal to a1, which means an equality must hold here, which means an equality must hold here as well. Namely, this means that k can either be 1 or 2. Not necessarily, it just means that an equality must hold somewhere here. And how do we know that k is either 1 or 2? I'm actually rushing over this. Let's assume k is greater than or equal to 3. Then we know this. Then we know this strictly, in fact. And then we will get a contradiction if k is greater than or equal to 3. So we know that via proof by contradiction that k is less than 3, i.e. k is either 1 or 2. And now if k is 1, then we know a1 plus a2 times d is equal to 3a1. We know that d can either be 1 or 2. If d is equal to 1, we would get 2a1 is equal to a2, a contradiction because this is supposed to be less than a1. And if d is equal to 2, we get 2a2 is equal to a1, which is okay. And in the other case, we get d a1 plus a2 is equal to 3a2. Again, here we have only cases for d's 1 and 2. For d is equal to 1, we get a1 is equal to 2a2, which is okay. For d is equal to 2, we get the same contradiction we got before. And now in both of these cases, we know that the final result is a1 is equal to 2 times a2. And now we finish it off with a2 plus ai divides 2a1. Here I is greater than or equal to 3. And now from here, subtract once, we get a2 plus ai divides a2 minus ai. This is greater than 0, but this thing right here is not greater than or equal to this thing right here, which leads us to a contradiction. Now, given that our original assumption led to a contradiction, this means that our original assumption was false. Namely, this means there do exist indices I and j such that ai plus aj does not divide any of the numbers 3 times a1, 3 times a2, or 3 times an. And as always, thanks for problem solving.